What's the limits of integration? 0 to 5, yes. That's what a plate is, 0 to 5. 62.5. That change in x is just a dx. You got a 4/5 times x, but you also have a 5 minus x. And again, we'll just set it up. We know this answer would be in pounds, right? I know you can do that interval.
What shape is the tank again?
This tank right here is just a triangular shape.
Like a cone or?
Oh, no, no, no. I'm talking about just a plate. I got you. It's not
Oh,
three-dimensional.
okay.
And I just want to make sure, we're going to just think of a plate. Like even before when I had that aquarium, you're like, well, that aquarium, we'd only get the hydrostatic force against like one side or another side.
So why did we take a rectangle slice?
Because we got to sum up all the different forces in here. They'd all be the same. And with this, that right there, if you think in trapezoid, it's infinitely small, we got to think. So that's how we're able to know it. You can still call it change in height going up. So good question. I know you're like, we can't think of like, does it look like that? It would be just what? It's this infinitely small, right? Just an infinitesimal piece that's like that. And that's why we call it change in x, in terms of the width of that. You can call it strip, but we give it a little size so we can see it. That's what we use. This would go with a triangle. If it was even like a circle, we'll still take these rectangular strips each time with all these problems with hydrostatic force. Cool. Hey, can I erase this? All right. Hey, one more. And this one I'm going to have to drop lower because I'm taking this problem from the book. This was in meters, so here's the surface level. I'm just going to drop a little lower. There's the surface level. All right, surface level of the water. This has a semicircle shape. Just like that.
So the plate is outside of the water?
Part of it. And they tell you how much is out of it. 1 meter. Everyone is out of the water. 1 meter of this plate is out of the water, sticking above the surface level. And the entire diameter of this semicircle here, and keep in mind this is a plate, is 6 meters. Those are the only dimensions they give us. They want us to get the total hydrostatic force against that plate. You go, well, part of it's out of the water. True. So that's going to be important, everyone, when we're talking about like the setup of the integral, whichever way we scale this thing, we're only going to be concerned with the limits of integration going from here down, right?
Is this assuming a perfect semicircle?
Yeah, perfect semicircle. A perfect semicircle, what would be the radius then? Because that's going to be important to us. All right, so and the radius is 3, he says. Very
That
good.
would mean that the part that submerges is only 2 meters.
That's right. Now we got to decide where to scale this. Do you remember with work, we dealt with something? Now I know with work, everyone was a tank that was like a sphere. Do you remember where we scaled it? From the middle. So and that's what we're going to do with this. And you go, well, where's the middle? Well, because it was a semicircle, we're going to scale it right from the top of that. That's where the widest region was of this semicircle, in terms of the radius. That's where the radius was the greatest. So I'm going to scale this x equal to 0 right here. Even though it's above the level of the water, okay? Just keep in mind, there's your surface level. So there's x equal to 0 right here. So what's x equal to right there? 1. And eventually at the bottom of the plate, what will that equal? At the very bottom, I want to make sure this lines up. I'll just step away.
3.
It's 3. X equals 3. I can just make that more vertical. Yeah, I'll put it down. X equals 3. So there we got it scaled. That's how we'd scale any type of semicircle or even a full circle. If there was a full circle submerged in water. Okay. So I like how we scaled it. Let me put this up here. D for density. Because it's just dad, right? We're talking about the force. And we'll get one strip. D for density. A for area. D for depth. But I need one strip. How about right here? And this strip. Oh, Sean, similar to the last problem. Now it's like a little what? On the side. But it's just, in terms of its width, we're saying it's infinitesimal. That's what we call it change in x. Because we're going to sum up, send a limit towards infinity, an infinite amount of these. I'll pull it out here. It's another rectangular shape. We give it a little thickness so we can really see it here on this green board. What's that width right there? Change in x. I'm going to put W again. This is now, this density, everyone, I'm going to have to use this right here. What's 1,000 times 9.8? So I'm going to put that here, okay? Because we got everything in meters, I'm going to have to use 1,000 kilograms per cubic meter times 9.8 meters per second squared. So for here, I'm going to use 9,800. If you want to put the units, you can. The area is change in x times W. And when we'll come back to this W. We'll figure out that W. What's the depth though? And then when I say depth, I'm saying depth below surface level. It's going to be similar to this.
X minus 1?
Man, you're so close. We usually, oh no, it is x minus 1. You're exactly right. I was thinking someone might have said 5 minus x or 3 minus x. You nailed it. And let's check it too. I mean, this depth, he says we're going to use x minus 1. Can we check this? So this right here, everyone, this was located at x equals 2. Armando nailed it. Let's check to see he's correct though. If you substitute a 2 in here, what's 2 minus 1? 1. Isn't that 1 meter below the surface level? And how about right here? You plug in a 3. How far is this below the surface level? You put a 3 in there, 3 minus 1 is what? 2. So great job. I was concerned someone might think 1 minus x. That would give a negative value. So we got everything. Here's the challenge. What are we going to call the width? Because it's changing. The width keeps changing, as we can see, throughout this plate we have that's submerged. So, you remember similar to when we did a sphere with work? We can talk about this as the radius. What was the radius? 3? I'd use 9 minus x squared, right? And it would just change. But the only thing is, in this problem, different from the sphere, this is an entire diameter. So how do you get diameter from radius? Yeah, multiply by 2. So this is what we're going to get. In terms of that width, 2 times. This is going to be our W. We'll put it right in here. We're going to call the width 2 times the square root of 9 minus x squared. Now I want us to check this. Because this is what we used when we dealt with this at work. Can we check it? Plug in a 3. Let's start there. What would be the width of the strip right there? Jessica, I don't see a strip. Well, let's see what happens. I plug in a 3. What's 9 minus 3 squared? 0. Let's check it right here at x equal to 2. At x equal to 2, you get 9 minus 2 squared, which would be 9 minus 4, square root of 5 times 2. You just got that entire length. That would be the length of that rectangle. Cool? Awesome.
Is it always 9 or it's just 9 because it's 3 squared?
Oh, it's not always 9. It's 9 because it was the 3 squared. So hey, let's pretend the radius was 5 for this problem. And it's scaled some way. This would be 25, right? Isn't that cool? It would always give us that width. Different from the, if you recall the work problem we did with it was a spherical tank. We didn't have to do this too. Because we only thought about these slices and pi r squareds. We were thinking of volume. We're like pi r squared, pi r squared, pi r squared. Because we're doing length times width, we're going to think of this entire distance right there. And we're like, from here to here is going to have to be 2 times 9 minus x squared. Awesome. Hey, can we check one more spot? I was just curious. What happens up here at x equals 0? How long is that? It should come out to be 6, is it? 9 minus 0, what's the square root of 9? 3. What's 3 times 2? 6. And there we go. I'm going to put it right here. We got the width. I got enough room right there. I'm going to put 2 square root 9 minus x squared. And so our total work, or excuse me, not work, total force, our total hydrostatic force against that plate is 9,800. Okay, you're the dx. We got a 2. We got a square root of 9 minus x squared. And we got this x minus 1. And you can see with this problem, it'd be appropriate for this definite integral. We're about to set these up to make it a definite integral that you could use technology to figure out this actual answer. The answer, would it be in pounds or would it be in newtons? Yeah, this would be a total force and the answer would be in newtons. But it'd be appropriate to use technology to this in terms of setting up the definite integral. But one more thing, everyone, we haven't figured this out yet. Be careful. Is it 0 to 3? We're talking about where it's submerged. Maybe we should shade. Where was it submerged?
1 to 2?
1 to what? We got to think the entire plate that was submerged. 1 to 3. Does anyone see that? This was all underwater. So the portion that's underwater, there's going to be a force, that hydrostatic, right? Hydrostatic acting on that plate 1 to 3. And boy, the answer will be in newtons. I know you can do this integral. Type it into your chat E3s or 84s. Great job.
Also, where'd that 2 come from?
That 2 came from in terms of, we had to think of the entire width of this rectangle. Let me go in here again, William. Right here. This strip. If I didn't have the 2 there, we would only be saying the width from there to there.
Okay.
Similar like when it came to, remember we dealt in work, it was a spherical tank. We didn't have to put that 2 there because we were looking at slices that were actually, she was saying 3-dimensional, pi r squareds. We were thinking of all these discs, and radius. But with this, we're talking, this strip is a rectangular strip. So we go, what's the entire length from this side to that side? It'd be 2 times this. And that would work with any type of semicircle plate or a full circle plate. For those widths of every strip, you'd be 2 times square root of, you could just do the radius squared here. Every time. It would work with any single circular plate or semicircle plate. Cool? Yeah, but I remember when I was a student, William, I always remember, I'm like, when it came to hydrostatic force, don't forget that too. Because it was different from the work problems.
66,980 newtons, does that sound about right?
Is that right? I don't know.
Yeah.
No.
Did you get the same? I'll put it down. What'd you get?
66,980.
66,980 newtons.
Are we going to have to deal with putting them in joules or no? Because we're not.
Nope. Great question. I know, this is so similar to work problems. Work problems were in joules because what's work again? Not just force. Work is force times distance. And that's why we put joules with that. These answers will either be in newtons or they'll be in pounds. And what's the 2 numbers you always use for density? 1,000 times 9.8, 9,800, or 62.5. And sometimes people get so concerned about the units in there, we're like, no one knows what's going to happen in the end. That's it. Is that it going there? Also, bless you. Are you going to raise? Evan, great job. Great questions, too. Such a neat section, though. Where we can see, calculus being applied in real life. We're now going to go into section 9.1. All right. This is differential equation. The author titles it Modeling with Differential Equations. You're going to notice this section compared to the one we just talked about. It's not a heavy section, but it does give us a nice introduction to what differential equations are all about. And then we're going to use these differential equations in sections 9.3. We'll even look at differential equations 9.4. So a differential equation, this is just one example. I'll put DE for a differential equation. Something like this. How about the rate of change of a population with respect to time? The rate of change of a population with respect to time is proportional to the size of the population. But that right there is a differential equation. Why? Well, it's got the derivative in there, right? It's got an equal sign equation, and I have a derivative here. This is a differential equation. But what we're looking at, if you take differential equations, you'll deal with a lot of this, is what's the solution to the differential equation? And by solution, I'm talking about what would P equal? Can we find it? Is there just one answer, or there's more than one solution? And many times out when you get many solutions with these problems, you can get what we call a family of solutions. And you change a constant, and you can make like graphs of all the different solutions.
That's a derivative. Can't you take the integral of that?
Exactly, because you would take the integral with this. There's only one thing weird about this when you just go, okay, integrate it.
Yeah, but another variable.
If I put this, think of that as y and that x, look what you have. dy dx, k, y. What's weird about this, we're going to have to think of a new technique. Don't worry, it's introduced in 9.3. The y's are on the left and the y's are on the right. That's not going to work. We're going to have to collect all the y's on one side and all the x's on the other side. Cool? Not hard though, because that's what we'll do in our first step. So Armand, I want to point that out. You're definitely right. You're saying you're going to have to integrate this. You're going to have to do some type of integration on either side of this equal sign to get your solution. Or I should say solutions, plural, because you can get a family of solutions. So what's neat, I think a lot of you are eager right now, let's do it. Well, we'll do it before you leave. What they wanted to do was just get you to start modeling this. Cool? And then before you leave, let's come back to this and go, can we figure out what would be the solution to this? Now, hey, there are things in this light, everyone, in real life where the rate of change of the population, which is change of population with respect to time, rate of change of population is proportional to the size of the population. Okay, this can happen with bacteria, but in many, many circumstances this can actually happen. We're going to figure out what happens with that and solve for P. Cool? So we'll come back to that. Don't worry, I don't want to leave you hanging, but that gets introduced in 9.3. Hey, before we do that, they give some problems in 9.1. And try this. I will sit down here and hold up. Y equals sine of 4x. And I'm going to give you some choices, A and B and C and D. Okay, here's a differential equation. Oops. My body. Here's another one. Another differential equation. Those are second derivatives though, right? It's still a differential equation. Y over 6 and y double prime equals negative y over 6. My question is, this right here is a solution to which of the following differential equations? So y equals sine of 4x is a solution to which of the following differential equations? So I'll just put DE for differential equations. This is how the textbook introduces this section. You start with problems like this, just to get you used to this. Remember, some of these differential equations can have more than one answer. They just want you to start out and figure out, well, which one would this be a solution to? How could we go about this to solve this? It's one of the four, as they're indicating. Any suggestions? That was right. You guys take the second derivative. We'll go off this side, find the second derivative of this, And we'll go back in, substitute in each one of these scenarios. We're going to see which one works out correctly. Where the left side is equal to the right side. Where you can write left-hand side equals right-hand side. Does everyone agree? That's how we're going to check this. I do want to point out these differential equations were given to you. Some of these might have more than one answer. This might not be the only solution. I know this is trigonometry, but it might be something else to solve. So, let's go over here. What is y equals sine of 4x? What's y, Brian?
Cosine times chain rule 4.
Yes, chain rule is positive, right? We need the second derivative. What's that? Negative 16 back to a sine of 4x. So let's go through here. We'll substitute this for every y double prime. What are we going to substitute for the y's though? Yeah, there you go. There's your y. We'll substitute this for y. We're going to substitute this for the y double prime and see which one works out. That's how we're going to approach this problem. As they introduce differential equation to us in this section. It's like, how are we going to approach this? That's how we're going to do it. We'll just check and see which one it works out. I know, you probably like this is kind of a lame problem. We'll come back to that cool thing of figuring out what y is. From that last one. Is this it? It's negative 16 sine of 4x equal, oh, and when I copied this incorrectly. These should all have 1s in front of the 6s. I apologize. Because it would have been E, none of the above, right? Someone agree? Those are 16. Well, is this the answer? What do I substitute for the y? Alright, does left-hand side equal right-hand side here? Left-hand side equal right-hand side, that would be no. Which one is it though? B. It's B. It's B, everyone. Negative 16 sine 4x equals negative 16 sine of 4x. But I don't let something like that stump you during a test. Sometimes it does. It's like, oh, I just got to take the derivatives and substitute. That's exactly right. But looking at the problem, you might sit there for a while going, I don't know what to do. And you're just going to go and check through A, B, C, D. A problem like this is number 5 in the textbook. I put it for practice. I don't want to do it because it's an odd problem and the answer's in Bob right back a book. But they did the complete opposite. What they did was they presented a differential equation and they said, which one of the following, A, B, C, or D, is the solution to this differential equation? Well, again, what do you have to do? You're just going to get those derivatives and just keep substituting and see which one works out correctly. The one that's going to be the answer is when the left-hand side is equal to the what? Right-hand side. Cool. So that's number 5. So this problem right here is like number 5 in the textbook.
Since you said there's multiple solutions, we have to keep substituting into each one until we find which ones are solutions?
Oh, good question. On a test, I'm going to make sure there's only going to be one option. There's going to be one solution to it. So once you find it, you can stop. The textbook did the same. So I want to point that out. Armando, number 5 from the textbook, they got an A and a B and a C and a D. They did the complete reverse though. I want to point that out. They completely reversed this. They gave a differential equation here. Then they gave possible solutions and they go figure out which one of these is a solution to that. But yeah, that's true. Sometimes a differential equation, there can be more than one answer to something. There can be more than one solution. But don't worry, that's for differential equations course. Right now we're just going to model them. Alright. That one. Try this one. That was like number 5. This one's like number 3. So I wanted to do some problems like the textbook because it's an interesting section, but if we don't do some of these, you might go home going, how do you work these? How do you start these? Where do you begin? Alright. And I want you to find the value of R. R is just some constant. Find the value of R such that y equal to e to the rx is a solution to the differential equation. Here comes your differential equation. dy dx minus 6y equals 0. And by the wording here, Armando and everyone, they said find the value of r. It looks like there's going to be only one value of r that makes this work. But again, a problem like this can sometimes just have someone on a test to get all the challenging problems. They get to this, they're like, I didn't know what to do. I didn't know where to start. It's going to be similar to the last problem. Where do we start? What do I do with this?
Taking the derivative.
You take the derivative of that. We'll substitute it there. What are we going to substitute for that y? That right there. And then when that r is just a constant, we're talking about some constant r. So let's go off to the side. Y equals e to the rx. Here's the only challenge of this problem. What's y prime? What is dy dx? R e to the rx. Chain rule. R e to the rx. Outstanding. True? Well, that r is just some constant. So I'm going to put that here. Minus 6. What goes here? I want to be careful I don't put in the wrong thing. What's y? Is y r e to the rx or just e to the rx? Excellent. So I'm going to put that here. And we just got to solve for what letter? R. But sometimes that ought to stump someone. They're like, I didn't know how to solve. How would you solve this equation for R? Starts with an F. Not a bad word. Starts with an F. Factor, right? Let's factor. What can I factor out of that? Let's factor it out. That's what bugs students. It gets in their way. Factor it out. Get it out of the way. And what are you left with? R minus 6, and it's just going to stand out to you, that solution. What's the R value? If r minus 6 equals 0, you factored r equals 6. You got it? Now, can we talk about this? Does this have something? If you didn't know this, I'm going to put it in your notes right now. E to anything will never equal 0. I'll show you the graph. What's the graph of y equal e dx look like? Does it ever hit the x-axis? Y equals e dx? Never hits it. So e to the 2x, e to a negative 2x will never, ever, ever equal what? 0. In fact, you know what? E to an rx, whether r is positive or 0 or negative, will never be negative. Do you want to put that in your notes? It's just something that can help you out. E to the rx can never equal 0 for x values, and e to the rx can never be negative. Well, that's y equals e to some what? 2x, 3x, 4x. What's y equal to e to the negative x look like? It does this, right? You know, if this was like some negative number here. But it still never hits the what? The horizontal asymptote, right? The horizontal asymptote is y equals 0. It never gets there. So we ignore this, don't we? Can't equal 0. Not equal to 0. Never. No x values to negative 0. Was everyone aware with that? Well, I did try to give you 100 of these, you get it. I did want to do the problem out of the book, though. I'll change it up a bit. Find the values of r. Such that y equals e to the rx is the solution to the differential equation 2y double prime plus 7y prime plus 6 equals 0. And don't forget, e to the rx can never equal 0, right? Never. So what do we need to do here? I noticed they said values, so there could be more than one answer. This is also like number 3. This is also like number 3.
You have to take the
the best. So what's the second root? There's y prime. I can believe that. What's y double prime? R squared e to the rx. Outstanding. Sometimes people think they need product rule. You don't need product rule here. Just the chain rule. That r is a constant, right? All right, you ready to substitute? What goes here? R squared e to the rx. What goes here? R e to the rx. What goes here? 6. Let me make sure I copy this correctly. Oh, I apologize, everyone. Next to the 6 had a y. I apologize. Next to that 6 had a y, so what would go over there, right there? Sorry about that. There was a y right next to that 6. Because otherwise, we wouldn't be able to factor out the ERX. Can we factor out the ERX now?
Yeah.
Yeah! Alright, what's left over? 2r squared.
Plus 7 plus 6.
Alright. Oh, we gotta factor that. So let's factor that. When we're factoring 2r squared plus 7r plus 6, 2r and r, these two numbers got multiplied to 6, right? We're factoring one of these case 2 trinomials. What two numbers multiply to a 6? 2 and 3.
6 and
2 and 3. Let me try the 2 and the 3. 2 and 3. Hey, if I want to make sure I factored that correctly, I can check it by FOIL. Will you help me check by FOIL? Just to make sure we factored it correctly, because I could have had a 6 and a 1, right? Let's see. 2r squared plus 4 plus 3r is 7r. We got it. So what are the answers? There is more than one answer. Let's start here. What's this? Nothing. True? Nothing there. How about here, though? You get an A for your house? I should show that in case people know how that fraction came up. 2r plus 3 equals 0. Subtract the 3. Negative 3 halves. And what's r equal to here? Negative 2. Cool. All right. Hey, 3B, I won't do that now, but they do ask you, they have a show problem. A show problem is like a mini proof, where you just got to show that it comes out true. They want you to show that this right here is also a solution.
What number was this one similar to?
This one was just like number 3. I used a different differential equation now, but it was similar to it. Hey, on number 3B, we won't do it now, but I want to mention, they have the word show.